Hey everyone, today we're going to be talking about the derivative of the sine of x. So before we begin, I just want to say that we'll be using some concepts that I mentioned in my last video, so if you haven't checked that out, be sure to take a look so you don't get lost. Now, let's get on with the video. Alright, to start things off, let's say that we have a function y is equal to the sine of x. Now, using our derivative equation that we have from before, let me just write it. We have dy over dx is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So in this case, since our f of x or a y is equal to the sine of x, we can write this as the limit as h goes to 0 of the sine of x plus h minus the sine of x all divided by h. Now, before, this was a lot easier to simplify because something like x plus h squared, we know how to simplify using FOIL. But the sine of x plus h can't be simplified in the same way. So in order to take the derivative of the sine of x, we first need to find the identity of what the sine of x plus h is actually equal to. Now to begin our proof, let's start with just a basic right triangle. So here's my right angle. And let's say that we can establish some angle which we'll call theta. And we can also say that this hypotenuse has length 1. Now to solve for the other side lengths, we can use trig functions. We know that we'll have a cosine of theta being equal to the adjacent side over the hypotenuse side. So I'm going to call this side length x and this side length y. And we can say that the adjacent over the hypotenuse is equal to x over 1, which is equal to x. And that means that this adjacent side length is equal to the cosine of theta. And we can also use the same process with using the sine of theta for our opposite side length. So we have the sine of theta is equal to the opposite over the hypotenuse, which is equal to y over 1, which is equal to y. So this is just equal to the sine of theta. And using the idea of cosines and sines, we can solve for the sine of the sum of two angles. Now I'm going to draw the same right triangle as we had before. And this will be the right angle, and this will be angle theta, and it'll have hypotenuse length 1. But this time I'm going to make another right triangle where the hypotenuse of the triangle we have drawn here will be the base of this new right triangle. So it's going to look like this. The right angle here. And let's say that we have some angle phi here. So if we were to create a triangle with angle theta plus phi, it would look like this. And I'm drawing it here in blue. So in this light blue color, we can see that this triangle has angle theta plus phi. And one important note here is that the hypotenuse of this triangle in blue is equal to the hypotenuse of the triangle with angle phi, and we'll be using that to help us with our proof. Now what I'm going to do to make things easier is I'm going to redraw our diagram. So we'll have our right triangle here with angle theta, and it's going to have hypotenuse length of 1. And as we know from before, that means that the adjacent side length is the cosine of theta, and the opposite side length is the sine of theta. I'm also going to redraw the right triangle that had the base being the hypotenuse of this triangle with angle theta. So it's going to look like this. And we'll have our angle phi. And I'm going to redraw our outline of the light blue triangle that had an angle of the sum of theta and phi. Now we know that the hypotenuse of the triangle with angle phi is equal to the hypotenuse with angle theta plus phi. So that's one key piece of information that we should keep in the back of our minds. Now, if we look here, I'm going to draw a line connecting from the edge of the triangle with angle theta and the big blue triangle. We can see that a part of that opposite side length is actually composed of the sine of theta. So what we're looking for is just this missing piece here. And we can actually see that by drawing the black line, we have created another right triangle. So that means if we can find some adjacent side length right here, then we can add that to the sine of theta, and then we'll have our opposite side length and we'll have our hypotenuse side length. And that'll give us what we need to solve for the sine of theta plus phi. So let's see if we can try and solve for these values. If I draw the triangle with angle phi right here and label my knowns and unknowns, we know that there's a right angle here, there's some angle phi here, and this triangle has a base of 1. And in the same way, in the same process that we had from before, we can solve for the missing side lengths using just an angle and one of the side lengths. So the cosine of some angle, in this case phi, is equal to the adjacent side over the hypotenuse side. And we know the adjacent side is 1. Let's call the hypotenuse side h. And let's call the opposite side, let's call that r. So the adjacent over the hypotenuse is equal to 1 over h. And rearranging our variables to solve for h, we will get that h is equal to 1 over the cosine of phi. And we'll keep this in the back of our minds because this is what we're looking for. And we can also solve for the sine of phi. So we'll get the sine of phi is equal to the opposite over the hypotenuse, which in this case is equal to r over h. And solving for r, we'll get that r is equal to the sine of theta, or the sine of phi times h. And we said that h was 1 over the cosine of phi. So r is equal to the sine of phi divided by the cosine of phi. Now before we take a look at the small right triangle that we created in our diagram and the top right, we need an angle to work with. So let's see if we can use our bottom right triangle as a reference point. We know that a triangle needs to have 180 degrees, and for our bottom right triangle, that'll be equal to the right angle, which is 90 degrees, plus theta plus some mystery angle, which I will label as A. And solving for A, we'll get that that is equal to 90 degrees minus theta. We can also solve for this angle here because it creates a right angle here because of the rectangle formed with these lines. So a right angle has 90 degrees, and we know that this angle A is equal to 90 minus theta, so that means that this angle here is just theta. We can also solve for this angle right here because this is creating a right angle from the triangle with angle phi, which means that this angle will be 90 degrees minus theta. And finally, we can solve for the angle at the top because we have a right triangle and we have two angles, and that means that it'll be 90 degrees plus 90 degrees minus theta, which means that the top left angle is just theta. And using this information, we're ready to solve for the height of this triangle. Now let's redraw the triangle we're looking at. So we'll have this length here and this hypotenuse and opposite length here. And this triangle will have an angle theta and a right angle here. Now we also actually know the hypotenuse of this triangle because the hypotenuse of this triangle is equal to the opposite side length of the triangle with angle phi. And we know that that is just equal to the sine of phi over the cosine of phi. And using these two known values, we can solve for the height. So we know that the cosine of an angle is equal to the cosine of the angle is equal to, in this case, theta, the adjacent side over the hypotenuse side. And if I label this as side length z, then we'll get that the cosine of theta is equal to z over the sine of phi over the cosine of phi. And to rearrange that real quickly, we'll get that this is equal to z times the cosine of phi over the sine of phi. And solving for z, we will get that z is equal to the cosine of theta times the sine of phi over the cosine of phi. And remember, this is all side lengths. We have all of these trig functions like cosine of theta, sine of phi, and all that, but we're looking at side lengths. So even though they are complicated, remember where they're coming from. So now we have a known value for our z, which is the height of the triangle, and that's what we're looking for. So labeling that as z, which equals the cosine of theta times the sine of phi over the cosine of phi, we are ready to solve for the sine of our big triangle because we have a known opposite side length, which is the sum of these two values. So the sine of theta plus the cosine of theta times the sine of phi over the cosine of phi. And we have a hypotenuse, which we know is equal to 1 over the cosine of phi, which we found from before. And using this, we're ready for our final sine equation. So let's draw our big blue triangle. So let's draw that here. We'll have the big blue triangle with right angle here, and it will have an angle theta plus phi and a known hypotenuse of 1 over the cosine of phi and a known opposite side, which is the sine of theta plus the cosine of theta times the sine of phi divided by the cosine of phi. So, using our trig functions, we know that the sine of any angle, in this case, the sine of theta plus phi, is equal to the opposite over the hypotenuse, which for this case just happens to be that whole mess up there. So we'll have the sine of theta plus the cosine of theta times the sine of phi over the cosine of phi. And this whole thing is divided by 1 over the cosine of phi. Now to simplify this, what we need to do is multiply by the reciprocal in our denominator. So we'll have the sine of theta plus phi is equal to the sine of theta plus the cosine of theta times the sine of phi over the cosine of phi, and this whole thing is multiplied by the cosine of phi. Now, if we distribute our cosine of phi, we will have the sine of theta plus phi is equal to the sine of theta times the cosine of phi plus the cosine of theta times the sine of phi over the cosine of phi times the cosine of phi. And these two cosines will cancel, and we will be left with our answer, which is the sine of theta plus phi is equal to the sine of theta times the cosine of phi plus, and I'm going to write the sines first, so it'll be the sine of phi times the cosine of theta. And finally, we have the answer that we're looking for. And using this identity, we can solve for the derivative of the sine of x. Now, let's rewrite our derivative equation so that we can solve for the derivative of the sine of x. So we'll have dy over dx is equal to the limit as h goes to 0 of our function, which is the sine of x. So we'll have the sine of x plus h minus the sine of x divided by h. And now we know that this is equal to the limit as h goes to 0 of the sine of x times the cosine of h plus the sine of h times the cosine of x, and this is minus the sine of x, and all of this is divided by h. And what I'm going to do is group like terms together. So we'll have the limit as h goes to 0 of the sine of x times the cosine of h minus 1, because we're taking a sine of x out of the sine of x. So when we multiply 1 by the sine of x, we're left with the sine of x. And we add the sine of h times the cosine of x. And this is all divided by h. So we have one last thing to prove before we can actually finally solve for our derivative. And that's we need to know what the sine of h and the cosine of h are actually equal to. And to do that, we are going to graph them. So let's draw our function right here. So we'll have the sine of x looking something like this. So let's just write out our function. We'll have y is equal to the sine of x. And this is all great. But if we draw a y equals x graph very close to it, we can see that these two graphs are nearly identical for very small inputs of x. So drawing this here, or writing this here, we can say that for small inputs of x, these two functions are identical. So saying that the sine of x is equal to x is okay because we're working with limits. We're working with inputs that are going to 0, which means that they're going to be very small. So generalizing these two equations as being equal to each other is okay. And if we were to do the same thing for our cosine of x graph, we'll have something looking like this. So we'll have y is equal to the cosine of x, and drawing a y equals 1 equation, which is just the horizontal line, y equals 1, we can see that for very small inputs of x, these two functions are also nearly identical. So once again, for small inputs of x, it's okay to make the generalization that the cosine of x is equal to 1. Because we're working with limits, this is okay. So now, plugging this back into our derivative equation, we are ready to solve. So plugging this back in, we will have that the limit as h goes to 0 of the sine of x times the cosine of h, which we now know for small inputs of h is equal to just 1. So we'll have 1 minus 1 plus the sine of h, which we know for small inputs is equal to h, and then times the cosine of x, all divided by h. So simplifying this, we will have the limit as h goes to 0 of 1 minus 1 times something is just 0. So we'll have 0 plus h times the cosine of x divided by h. Now these h's are going to go, and we will be left with just the cosine of x. Now this was a very lengthy process where we first proved the sine of the sum of two angles, and then we proved that for small inputs of a trig function, we can generalize it as a linear graph. but this is the answer we are looking for. Thank you guys for sticking with this. In the background here, I have the proof simplified down for if we had a coefficient times the sine of x. It's the same idea. All you do is multiply by that coefficient and the derivative. So as we see here, a times the sine of x, a being any number, we'll just be having a times the cosine of x being the derivative. I hope you enjoyed going through this proof. It took a while, but hopefully it was helpful and that you now understand where this derivative actually comes from. As always, if you want me to go over something specific, just let me know in the comments and I'll do my best to help. And until then, I'll see you in the next video.